Alright, welcome back. So in this video, we're going to be talking about dimensionality reduction. I decided to include this video as well because I actually did dimensionality reduction and I would like to see how it actually tinkers with the model as well, like how the results will differ. And later on in the discussion part, we're going to do a bit of a comparison, right, between like the models. Okay, so what is it, right? It is the transformation of data from a high dimensional space to a low dimensional space, so that the low dimensional space representation retains some meaningful properties of the original data, ideally close to its intrinsic dimensions, right? And okay, so essentially, um, the problem with many input variables is that the performance of machine learning models can degrade, right, with too many input variables. If the data is represented as rows and columns, such as in a spreadsheet, the input variables are the columns that are fed as input to the model to predict the target variable. Input variables are also called features, right? Okay, so um, having a large number of dimensions in the feature space can mean that the volume of that large space is that space is large, right? And in turn, the points that we have in that space, the rows of data, often represent a small and non-representative sample. And this can dramatically impact the performance of machine learning algorithms fit on data with many input features, generally referred to as the curse of dimensionality. And it is often desirable to reduce the number of input features, and this reduces the number of dimensions in the feature space, hence the name dimensionality reduction. Okay, so yeah, okay, and then um, okay, so fewer input dimensions often mean correspondingly fewer parameters or a simpler structure in a machine learning model referred to as degrees of freedom, right? So a model with too many degrees of freedom is likely to overfit the training dataset and therefore may not perform well on new dataset. It is desirable to have simple models that generalize well and in turn input data with few input variables. This is particularly true for linear models where the number of inputs and the degrees of freedom of the model are often closely related. Okay, so there's like a bit of a relation between like the inputs, right? The um, you know uh, so taken from like okay, so like when dealing with high-dimensional data, it is often useful to reduce the dimensionality by projecting the data to a lower dimensional subspace, which captures the essence of the data, right? Which is called the dimensional reduction. And okay, so um, we mentioned, right, the essentially like how too many input features is generally referred to as the curse of dimensionality. And the fundamental reason for the curse of dimensionality is that high-dimensional functions have the potential to be much more complicated than low-dimensional ones, and those complications are harder to discern. And the only way to beat the curse is to incorporate knowledge from about the data that is correct. And yeah, so essentially, data dimensional reduction is a data preparation technique performed on the data prior to modeling, and it might be performed after data cleaning and data scaling, and before training a predictive model. Okay, and as such, dimensionality reduction yields a more compact, a more easily interpretable representation of the target concept, focusing on the user's attention on the most relevant variables. And okay, as such, any dimensional reduction performed on training data must also be performed on new data, such as the test data set, validation data set, the data when making a prediction with the final model. Okay, so okay, the most common method is the so-called feature selection technique that uses scoring or statistical methods to select which features to keep and which features to delete, right? And then we have four techniques right here. So we have the Pearson correlation coefficient, we have the Spearman correlation coefficient. Both take numerical inputs and produces numerical outputs. And then we have chi-squared test and Kendall-Tau test. The first one with categorical input and categorical output, and the latter one having categorical input and numerical input and categorical output, right? And then depending on whether the features of the data are numerical or categorical, and whether the target class label is numerical or categorical, the different feature selection from the above list can be chosen. Okay, so and then essentially the next one we have another method of dimensionality reduction. It is called the matrix factorization, which can be used for dimension reduction as well. So uh, principal component analysis, or PCA, is a matrix factorization technique to reduce higher dimension data to lower dimensions, and it preserves the direction with maximal variance, right? Okay, so because you would like to maintain variance as well. Okay, and then another one, we actually have what we call the manifold learning. So like techniques from the high dimensionality statistics can also be used for dimensionality reduction. In mathematics, a projection is a kind of function or mapping that transforms data in some way. And the technique is called manifold learning and are used to create a low dimensional projection of high dimensional data, often for the purposes of visualization. So the projection is designed to both create a low-dimensional representation of dataset while best preserving the salient structure or relationships in the data. And then we can also use deep learning neural networks. And it can be constructed to perform dimensionality reduction. So like a method called autoencoder essentially involves framing a self-supervised learning problem where a model must be reproduce the input correctly. A network model is used that seeks to compress the data flow of a bottleneck layer with far fewer dimensions than the original input data. Okay. Uh, The part of the model prior to and including the bottleneck is referred to as the encoder, and the part of the model that reads the bottleneck output and reconstructs the input is called the decoder. Okay, so like the autoencoder is kind of like an unsupervised neural network that is used for dimensionality reduction and feature discovery. And more precisely, we can say an autoencoder is a feed-forward neural network that is trained to predict the input itself. After training, the decoder is discarded from, and the output from the bottleneck is used directly as the reduced dimensionality of the input. Inputs transformed by this the encoder can then be fed into another model, not necessarily a neural network model. So yeah, um, so we have like the autoencoder, which is an effective framework for nonlinear dimensionality reduction. Once such a network has been built, the topmost layer of the encoder, the code layer, can be input into supervised classification procedure. Um, the output of the encoder is a type of projection, and like any other projection methods, there's no direct relationship to the bottle um, to the bottleneck output back to the original input variables, making them challenging to interpret. Right? Okay. All right. So essentially, there's no best technique for dimensionality reduction and no mapping of techniques to problems. Instead, the best approach is to use the systematic controlled experiments to discover what dimensional reduction techniques, when paired with the model of choice, result in the best performance in your dataset. Typically, linear algebra manifold learning methods assume that all inputs features have the same scale or distribution, right? And this essentially suggests that it is a good practice to either normalize or standardize the data prior to using these methods if the input variables have different